Okay, so what we're going to talk about today and tomorrow is going to be the fundamental theorem for line integrals. And so it's going to be really similar to this fundamental theorem from calculus, which is, and this is kind of the second form of the fundamental theorem of calculus, because you remember the first one is that the derivative of the integral equals the function. And this one is that the integral of the derivative equals the values of the boundary. The difference of the values of the boundary. I guess I should say it doesn't really equal it depends on it. But so that's the fundamental theorem of calculus. And what we're going to look at today is the fundamental theorem of line integrals and kind of all the implications that come from that theorem. Okay, so kind of without further ado, this is the theorem. Okay. And so what it says is that if we have a differentiable function, if we take the line integral of its gradient vector field, then all it depends on is the ends of the path. Notice we have like RB minus R of A, or F of RB minus F of R of A. So it depends only on the endpoints. Which is kind of like a big deal. Because what that means then is that the path in between doesn't affect. Like, notice over here, this is an integral over a whole curve C, and what this says is, well, the path doesn't matter at all. It only depends on the beginning and the end. Okay. And so let's kind of look at where this comes from and then look at some pretty significant implications of this. Okay, so the proof is actually pretty straightforward. So let's kind of think of, we have some curve C, and we'll say it's parameterized by a vector function R of t, and we'll just kind of say it's x of t, y of t, z of t. Okay, and so we already know that this dr right here, remember that dr equals r prime of t dt. So we know that we're going to want r prime of t, so let's kind of go ahead and just write out r prime of t, not r. So r prime of t, just to kind of write it generally, because we have these general functions, I'm going to write it as dx dt, dy dt, dz dt. And so remember that this is still a vector function. Okay, and then the only other assumption for this theorem was that f was continuous and had a continuous gradient. So if f of x, y, and z equals some function, what would its gradient equal? How do we write out the gradient as a vector? Yeah, it's just the vector of the partials. So it would be df dx, df dy, and df dz. Okay, so let's just kind of look at what this line integral is going to look like. Okay, so like I already said, we know we can change this to be the gradient f dotted with r prime evaluated, with respect to t. That's kind of that change to our parameter. Okay, and so again, sorry, when we switch parameters, we're also going to be kind of just now integrating from a to b, because we're all just in terms of t. So let's just kind of list out, write out these two vectors. So we're going to have dx, dx, dx dy, and dx dt. Start with dx dt, y dt, and dt. So let's take this dot product. We're going to have dx dx times dx dt. So remember, we kind of take like the first element and put them together, and then we add, oops, the wrong color here. And then we add, and we take the second two elements and multiply them and add. So we're going to have dx dy plus dy dt. And then we take the last two elements, which would be dx dt and then dt. And so does anyone recognize that? It looks familiar, right? Okay. No, so it's not quite, it's one of the like big rules we have. It's an application of a rule from the union partial. I'm going to write something really quick. So remember, we can think of f of r of t as kind of a function on a vector as f of x of t, y of t, z of t. Okay, and so then we want to take the derivative of this function with respect to t. What do we have to use? A certain rule. All this is like a direct application of the chain rule. So remember, when we're taking the derivative using the chain rule, kind of how it works is that we think of taking the derivative of the function with respect to the first variable, which would be df dx, and then we multiply by the derivative of that variable with respect to t. So that would be dx dt. And so then we would come down to the next variable, and we take the derivative of the function with respect to that variable, and then multiply by dy dt. And then the last one, because it's a function of three variables, we're going to have df dt times dz dt. And so what this is right here is exactly the same as this right here. Okay, so this is kind of our little interlude. And so what that tells us is that this big long expression is equal to the derivative of this function with respect to t. So if I bring this down with an arrow, all this integral equals is d dt of f of r of t. and when we have the integral of the derivative of a function, how do we evaluate that? So it would just be f of r of t evaluated from a to b, which is f of r of b minus f of r of a. And so, you know, we had to use the chain rule, which is kind of like one little step, and we use the fundamental theorem of calculus from way back in the day, right here, the very last step, you know, but we proved that if we have a gradient, we take the line integral of the gradient function, then all it depends on is the integral, which is pretty significant. You know, I think that's a pretty significant idea. Okay, so let's take an example. Let's take a look at an example of using this, and then we will kind of talk about some implications, which is what we're going to spend most of today and tomorrow on. Is just kind of talking about implications of this rather significant kind of result. Okay, so we have this force field here, this gravitational force field. You know, so we have the product of the masses and the gravitational constant, and it varies over the cube of the radius. And remember, we saw it written, I think, as negative mg over x squared, and then it was in the direction of, I guess actually this was negative, because this was like the force of gravity, and we said it was in the direction towards the origin. And I can't remember, did we go through and figure out like kind of what the function representing this would be? Because there's a way to show that this equals the gradient. I can't remember. Yeah, so we didn't quite go through that. Anyway, there's a way we can show that the function, like we want to find the function whose gradient is equal to this vector field. You know, because that line integral is in a vector field, and this gravity is a vector field. But notice when we're trying to apply this, theorem, the line integral is over the gradient field, but when we evaluate it, it's just using the function. Okay, so we have to kind of figure out what the function is going to be. And there's a way to show, and just for time's sake, I'm not going to go through it right now, but we can show that this function is just going to be kind of this little mass times big mass times gravity over the radius. So gravity is just going to kind of vary with the radius. And the force is going to vary with the radius squared. But, so this is where the function comes from. And if you kind of really wanted to like go through the derivative or finding the gradient, well, notice when we took the derivative with respect to x, we would kind of use the chain rule because this is, you know, we did that 2x on the outside, which would give us this, but then when we take the power rule, this is going to be to the 1/2, and so we get a 1/2, and that would cancel. And so it's pretty easy to show that this works out to be like negative x in NG over x squared plus y squared plus z squared to the 3 halves. And then here we have negative y in NG over x squared plus y squared plus z squared to the 3 halves. And then negative 3 in NG over x squared plus y squared plus z squared to the 3 halves. And so notice that we're going to have kind of this x squared plus y squared to the 3 halves, and this negative x, this negative x up here is the vector, the position vector, which would just be x, y, z. Okay, so this is going to end up being the correct function. And so let me see how to steal this function. Copy it again. For making this video, this is what it's not right there. Okay, and what we want to do is we want to calculate the work done between these points 3, 4, 12, and 2, 2, 0. Okay, so we know that work is just f dot of the dr. That's another good one. But we just showed that f is equal to the gradient of, this function right here, f, little f. And now we can just use the fundamental theorem, because we just want to take the value of 2, 2, 0 and subtract 3, 4, 12. That's just using the fundamental theorem for line SCLI. Okay, so what would f of, I don't want to spin down too much because they won't be able to see the function. Everything here anyway. It's spin down very much. So all we have to do then is find 2 squared plus 2 squared plus 0 squared. And then we're going to have minus 3 squared plus 4 squared plus 12 squared. So that's going to be equal to mg. We factor that out. And so we'll have 1 over, this is going to be 4 plus 4. So it will be the square root of 8. Well, yeah, which will be 2 square root of 2. Minus 1 over, so the square root of 3 squared plus 4 squared. So the whole thing is going to be 13. Yeah. So this equals 25, which equals 5 squared, and 5 squared plus 12 squared is another Pythagorean triple, which is 13 squared. So this whole thing is just going to be 1 over 13. I'm going to draw it as a vector. It's not, and so that's going to be the force. That's going to be the total work. What do you notice? Is 1 over 13 bigger or smaller than 1 over 12? Smaller. 1 over 13 is smaller. Yeah, I would think so. Yeah, this was, yeah, 13 is definitely bigger than 2 root 2. So then 1 over 13 is too small. So that means it's done positive work. So and so that's kind of the power of the fundamental theorem, is that we didn't have to worry about trying to, like, imagine trying to integrate this thing over some curve between these 2 points. Even just along a line segment between those 2 points would be pretty unpleasant. Okay. Yeah. Oh yeah. Yeah. Because it doesn't matter. All that really matters is where you're starting and where you're stopping. Doesn't matter how you get there. Yeah, that's true. Yeah, for like the path. But then again, the path doesn't really matter, because the vector field that you're in is going to be gravity no matter what. And this tells us that the path is kind of independent. So like, your gravity is going to do the same amount of work if you start up here and end up here, no matter if you like fly straight down that steep hill or if you like wind way down. Gravity's going to do the same amount of work. That's what's crazy. Yeah.
For the equation.
Yeah, exactly.
The field.
Yeah, it's all about getting good at accurate approximation. Okay, so that kind of actually, like, it leads well into this discussion. Okay, because this theorem has pretty, like, significant implications. And so imagine we have these 2 different paths, going through, I don't know, through 2 spaces, 3 spaces, however you want to think about it. I think we've already looked at a couple examples. We know that, in general, if we take the line integral of the same function over 2 different paths, we're going to get different, we should get different values. We expect them not to be equal. But what does this last theorem tell you? So if we have some continuous gradient field, and we have C1 and C2, different paths, but they have the same endpoint. So we'll say different paths. But initial point, we'll say initial point A and terminal point B. That's wrong ampersand. There we go. Okay, well then the line integral over C1 of that gradient vector field, we know that's going to be equal to f of b minus f of a, right? That's kind of the theorem we just proved. And likewise, when we integrate over C2, well, that's also going to be f of b minus f of a. And so then we know that these 2 are going to be equal, because they both end up having the same values. They just depend on the input. Okay, and so kind of in general, we don't expect them to be equal, but if it is gradient functions, if we're talking about gradient vector fields that are continuous, then we know that it's going to be equal no matter what the path is. Okay, so that's kind of the big significant implication is that if we're integrating through gradient vector fields that are continuous, then we don't have to worry about the path. We just have to worry about the endpoint. Okay, so what that means is that the line integral through a conservative vector field only depends on. Remember, what did we define a conservative vector field as? Yeah, that was last Tuesday or last Wednesday when we talked about vector fields. What is a conservative vector? So a conservative vector field F is one that can be expressed as the gradient of a function. Some real value function. Little that. In other words, if big F equals the gradient for some function little f, then we call big F conservative. That's kind of how we define it. And so what that means then is because it's the gradient, well, we know that integrating through the gradient only depends on the initial and terminal point. And so if a vector field is conservative, it is a gradient, and so it only depends on the initial and terminal point. Okay? So then kind of what we're left to figure out then is, well, how can we tell if a vector field is conservative? Because if it's conservative, then we know, well, all we have to worry about is the input. So we kind of have to think about how can we tell if a vector field is conservative. Okay, so what we can kind of do is if we can show that it's independent of path, then we know it's conservative, because then we know it only depends on the endpoint, and we know that kind of tells us that it's conservative. And so independent of path means exactly that. It means that if the two paths have common initial and terminal points, then the integral between those two is going to be the same. Okay, so it makes a lot of sense. What independence of path is. The path doesn't matter, just the endpoints. Okay? And so what does that tell you then about conservative vector fields? All conservative vector fields are they're all independent of path. Yeah, it is. That's kind of all conservative vector fields are independent of path. And so then what we can do, the contrapositive of that, for example, would be that if we have a vector field that isn't independent of path, like if we can come up with two paths between the same points that have different line integral values, then we know that integral is not conservative, for example.
Are there four terms
Yeah, there's the statement, there's the converse, the inverse, and the contrapositive. Yeah. Yeah, good old logic. Okay. So let's kind of take a look at this there. Because what this says is that we define a closed path as just being a loop. I like the word loop better, so I'm going to actually write a loop. And so all it means is it starts and stops at the same place. Okay? And so this theorem says that we can show that a vector field is independent of path if and only if every closed path has a line integral that comes out to be 0. Okay? And so let's kind of take a look at what this is going to entail. Because remember, if we have if and only if, what if and only if means is that if we assume that it's independent of path, then we know that this is true. We know that all closed paths integrate to 0. And also we know that if all closed paths integrate to 0, we know it's independent of path. Okay, so we kind of have to show that one tells us the other and that the other tells us the first. So if and only if theorems are a little tricky, but I think that we can go through this. It's pretty straightforward. Okay, so to kind of prove this theorem, the first thing we want to do is let's kind of assume, let's go kind of in the normal way, the way it's written. So let's assume that the line integral is independent of path. Okay, and what we want to show is that the line integral equals 0 over every closed loop. So that's kind of the proof going in the first direction. Okay, and this is actually really straightforward. So let's just pick some arbitrary loop. And we can really make it as arbitrary and general as we want. We don't have to worry about it. We can make it, you know. And what we can do is we can pick 2 points on this loop. Okay. So if we call this closed loop C and pick 2 points A and B on it, then we can define C1 and C2 and so notice that C equals the union of C1 and C2. So we can travel all of C1 and then all of C2. We will travel kind of that loop C. Okay? So what do you notice about C1 and C2? Or actually, let me say, what do you notice about C1 and negative C2? They're not quite the same. So C2 goes this way. We think of negative C2 as going this way. So this would be negative C2. So C1 and C1 and negative C2 have common initial and terminal points, right? So both C1 and negative C2 start at A and end at B. And so what that tells us then is that the integral over C1 of FDR equals the integral over negative C2 of FDR. This is because F is independent of path. We also know that the integral over negative C2 of FDR is going to just be equal to negative integral over C2 of FDR. So when we integrate in the other direction, the work is just going to be negative. And so then we know that C1, the integral over C1 of dr equals negative integral over C2. And so if we look back up at our picture one more time, to integrate over this whole closed loop C, all we have to do is integrate over C1 and then integrate over C2. So the integral over C, our closed loop of FDR, is going to equal the integral over C1 FDR plus the integral over C2 of FDR. But this equals the integral over C1 of FDR minus the integral over C1 of FDR, because those two are opposites, and that just equals 0. Okay, and so because C, so remember this was our closed loop, and so because it was arbitrary, this is true, is true, this is true. This is true for all closed loops. And so that kind of finishes the little triangle. So we finished the first part. So we finished the first part. Okay, so what we've done is we've shown that if it's independent of path, then the integral over every closed loop is going to be 0. And what we want to do now is we want to show the other direction. Okay, so the other step, the other step is going back. In the other direction. So in other words, we're going to assume that the integral equals 0 over every closed path C. want to show that the integral is independent of that. Okay, so we want to go in the other direction. So remember, what independent of path means is that if we have two paths, any two paths between 2 points is going to be, the integral is going to be the same. We don't have to worry about the path in the middle. So in other words, if we pick 2 points, A and B, and we have 2 curves going between them, C1 and C2, we want to show that integral over C1 of FDR equals the integral over C2 of FDR. Because that's equivalently showing that it's independent path. Okay, because again, these are arbitrary points and arbitrary paths, and so we're being general enough that this is kind of going to be true. Okay, but notice that this is equivalent to saying that the integral of C1 minus the integral over C2 equals 0. And so, does anyone have any ideas how can we show that? Close. So what is it that we know? What is the assumption that we have? What did we start off assuming this time? So we assume that a closed path equals 0. Okay? So notice that we can cook up a closed path by taking the union of C1 and negative C2. So if we assume we have negative C2 going this way, then C would equal C1 union negative C2. Okay, and so then we know that the integral over C is C equals 0. Because C is a closed path. And so that tells us that the integral over C1 of FDR plus the integral over negative C2 of FDR, because remember C equals the union of C1 and negative C2. We know that that equals 0. So then we know that F1 over C1 equals the negative integral over negative C2. Come on here too. We subtract that over the other side. But remember again if we're going along negative C2, that's going to be negative the integral over positive C2, and so that negative would cancel. And so then we get that integral over C2. And so, in other words, we see that the integral over C1 equals the integral over C2. And so since these are arbitrary, we know then that this integral is independent of path. And so that proves it going both ways. So we showed, first we showed that if it's independent of path, then the integral is over every closed path is 0. And then we also showed that if the integral over every closed path is 0, then it's independent of path. And so that kind of establishes this theorem. So this is where I was going to prove that. So I already did that. Okay, so let's kind of think about what that means then. Well, we know that from the beginning we know that conservative vector fields are independent of path because they depend only on the endpoint. And we also know that if something is independent of path, closed circuit equals 0. And so what that tells us is that if F is a conservative vector field, every closed path is going to have an integral of 0, which is what we saw earlier with the spell works this morning. Remember how both of those were closed paths because they made circles, and the integrals worked out to be 0 in both cases. So that's kind of the next big thing is that if we can show that it's a conservative vector field, then we know that the closed path is going to be, every closed path is going to have an interval of 0. Okay, and so I think that I want to stop here for today because this is a really good point to stop. So we'll go through this theorem tomorrow, and then we're going to look at a bunch of examples, kind of, not a bunch, but a few examples of using these theorems, kind of going through and deriving all these topics. Okay, so